Stat World! What up, Stat World? Just getting into my dark, emotional side, right? This whole quarantine thing's wrong. Let's do some stats, though, right? Take our mind off of it. All right, so grab yourself a clean piece of paper. Today's notes are old school. So fold it, not quite totally in half-C's, but almost in half-C's. We've done things like this before. I'm gonna fold it like to about right here. All right, so I get to teach you all about significance tests. Yeah. So let's go ahead and give it a quick title. This is 9.1 from your book. This is significance test. Who is that? I kind of look adorable. Goth for life. All right, so significance tests. We're kind of switching gears. For the last, 3 days now, you've been doing intervals with nets. But now we're going to leave the nets behind and we're going to look for evidence. All right, so draw yourself a little Billy Bell curve. All right, so again, we were trying to capture the truth by casting out our nets, right, with these confidence intervals. Confidence intervals. All right. And right, these were captures the truth. All right. Now we're going to be looking out here in the tails on both sides, and we're going to have magnifying glasses now. So I don't know, is this how you draw a magnifying glass? With a little shoop, shoop, right? Ooh, magnify it. So what we're going to be doing is look for evidence. All right, look for evidence. Since we're out there in the tails, we're looking for something that's small, right? Something that beats the odds, right? You shouldn't be out here in the tails. It's dangerous, kid. But if we do find something out there, then we have significance, right? So we're answering the question, is our sample significant? Did it beat the odds? Is it rare? You know, all that good stuff. Okay, so go ahead, draw a line. So that's your little setup. Now we'll get into the deets of it all. When we get into these significance tests, the very first thing you want to do is define your parameters. All right, so define parameters. All right, so your parameters for this section is going to be P, or it could be mu. All right, notice I'm not using the symbols for samples, right? So P hat, X bar, they're not a part of this. All right, this is P and mu. P mu. So P is the true proportion of, and then I would just put context here. So if your problem is about the true proportion of metal songs that are on your Apple playlist, yeah, then mu would be the true mean. True mean, and it's usually an amount, right? True mean amount, whatever, in context. All right. Okay, so once you define what it is we're investigating, right? What are we investigating? The next thing that comes in is the null hypothesis. The null hypothesis. What is the null hypothesis? Well, the technical definition is that it's just a statement of no difference. So a statement of no difference. The word null means empty, right? Null means not there. Null and void, cancel. So no difference. So in stats, we use this symbol H for the word hypothesis, and then a 0 here, which represents the nothing, right? The null. So this is our null hypothesis. Some people, when they see that, they feel like it says ho. Stop being immature. All right, it is the null hypothesis. All right, so it's a statement of no difference. The null hypothesis, you can also think of it as the claim that we're doing. It'll look like this, right? You'll have H sub O, and then you'll put a number here, whether it's the proportion or mean, depending on your problem. All right, so you'll put a number here. This number, when you're looking through the word problem, it's the claim. The claim being presented. So if I claim that there is 70% of metal songs on my playlist, right? That would be the claim. And you're like, wait a second, Hamilton, 70% on your playlist is metal? I don't think so. So the alternative comes into play. All right, so the next thing is the alternative hypothesis. All right, so your alternative hypothesis, we use H for the word hypothesis and a little lowercase a, the alternative hypothesis. This would be what we are looking for evidence of. All right, so oh, I put equals, wrong. All right, so the symbol here is gonna change. This is the claim. I claim that 70% of the songs are metal. And you're like, nuh-uh, we think it's more than that. Or maybe you think it's less than that. Or maybe, you know, I'm really not sure. Maybe it's more or less than that. So this symbol right here, we don't use equal. We use greater than, we use less than, or we use does not equal. All right. This blank right here, this number is still going to be the same number as above, right? Same numbers. But I'm going to put right here, this is the claim we are finding evidence for. All right. Okay, so we define what we have, proportions or means. We state what the claim is that's being presented to us. And then we put what we alternatively think is going on. We're like, nah, it's more than. No, it's less than. No, it's not equal to. So we have some other thing on our mind that we want to try and prove. Okay, so the way we're going to prove it is with a formula, which we won't get into until tomorrow. I just wanted to do the vocab for you today. But what our formula is going to do is it's going to look at Billy Bell curves. So draw yourself 3 Billy Bell curves right here. 1, 2, 3. And let's talk about the language here. If we are doing the greater than symbol, greater than would be on this side, right? Greater than. If we are on this side, we call this a right-tailed test. They also call these one-sided because you're only looking at one side of the bell curve. So right-tailed or one-sided if your alternative uses that symbol. Or we could use the less than symbol. If we use the less than symbol, then we're down here on Billy Bell curve, right? We are less than, we are left-tailed. Hi, Randy. Yeah, I'm doing math. Yeah, it's the neighbor. All right, Lily, he's gone. All right, so left-tailed, that would also be considered one-sided. Okay, they're gone. They just waved to say hello, and I look ridiculous. All right, so right-tailed, left-tailed, and the other option would be two-tailed. All right, if we look at both sides, that's when the symbol is does not equal to. So does not equal to, we look at both sides of our bell curve. We call that two-tailed or two-sided. My Lanta. Yeah, the neighbors saw me. I know, it's embarrassing. I'm barking too. All right, so back to what we were saying before the dogs and the neighbors interrupted our learning session. All right, so we defined what it is we're after. We wrote down our statements. we are investigating the bell curves for evidence of statistical significance, right? With our magnifying glasses, because it's going to be really small, right? It's going to be really small. I keep saying it is going to be really small. Well, it has a name. The name is the p-value, right? So I can fit the last thing on this page before I grab a new one. P-value. This is the evidence. The evidence. All right, so this is what we are looking for underneath our little magnifying glass there, right? The evidence. All right. So what is the p-value? The p-value, it's a probability, so it's a percent. It's the probability assuming the null hypothesis, HO, assuming the HO is true. All right. So the probability, assuming the null hypothesis is true, that the statistic we found is as extreme or more extreme than the one actually observed. Probability assuming the null hypothesis is true that the statistic we found is as extreme or more extreme than the one actually observed. All right. So in other words, it's the probability of the sample. So if we got something like 0.0002, we'd be like, whoa, the probability of this sample was like 0.002. This shouldn't have happened. Ludicrous. So if it shouldn't have happened, that's when we can start to decide which one we can go for. Did we find evidence that the null hypothesis was lying to us, that the HO is lying, and we could go with the alternative? Or do we not have evidence? Do we keep the null hypothesis until we have better research or a different sample? All right, let me grab another piece of paper so we can keep it rocking. Yeah. All right, so the next thing that we have to start thinking about is significance. So is our evidence, and remember, evidence is the p-value, right? So is our evidence p-value significant? All right, the way we find significance is by first setting a significance level. So set a significance level. All right, when you're setting a significance level, you should do it before you start taking your samples. Most studies, when you look at the fine print or the footnotes, they set their significance levels at 0.05. So if their sample is below 0.05, that's rare, that's enough. But if it was like a medical study, a drug study, they want to be extra sure, they're going to make their significance level even smaller than that. The symbol for our significance levels, by the way, is going to be this alpha, right? This Greek letter alpha, alpha. Consider it like a cut score. Anything under this cut score is significant, right? Anything under this cut score is significant. Okay, so let's see, most common. Oh my. The most common is alpha equals 0.05. So the most common is that 0.05. All right, so that is the one you're going to see most often as we go through these. Okay, so the conclusions here. I know it's kind of like, what is she talking about? I promise it'll all come together in the next few days with this. This is just getting your feet wet with it. So the conclusions that we're going to have here is you're going to compare your p-value. If your p-value is less than alpha, right? So if the p-value is less than, let's say, 0.05, then we have significance, right? If we have significance, then what we will do is reject the null hypothesis, right? If the p-value is smaller than alpha, we will reject that null hypothesis. If we're rejecting that null hypothesis, that means we're concluding with the HO, right? We're conclude with the alternative, right? The HA. Okay, well, if our p-value is greater than or equal to alpha, that means we really don't have evidence. This isn't rare at all. So if p-value is greater than or equal to alpha, we will fail to reject the null hypothesis, right? Fail to reject the null hypothesis. So what does that mean? That means, you know, the null hypothesis can still stay, right? The HO, the null hypothesis, still stands, but while the HO, the null hypothesis, might not be true, we simply do not have evidence to get rid of it. Let me read that back. The null hypothesis still stands, right? We failed to reject it. It's still going to be there. But the null hypothesis might not be true. Don't think because we didn't reject it that it's true. It just means we don't have the evidence at the moment to get rid of it. All right? So in other words, never accept the null hypothesis, right? Never accept the null hypothesis. So you want to make sure you're using this language right here. You either reject the null hypothesis, kick it to the curb and go with the alternative, or we fail to reject the null hypothesis. We let the null hypothesis hang around, but we never, ever, ever say accept the null hypothesis. So on the multiple choice, you better believe it, you're going to see some of them say accept the null hypothesis, don't fall for it. We never do that. We fail to reject it. We never accept it. All right. And here's a little saying I didn't come up with. It's been out there floating around for a while. I remember learning it when I first started statistics, but it's a little rhyme to help you with all this. If the P is low, and by P we mean p-value, so I guess I should clarify. All right, if the P is low, reject the HO. If the P is low, reject the HO. Okay, so again, we define what we're after, proportions or means. We write down what the claim is that's being presented to us, and then we give an alternative one, like, maybe it's more than, maybe it's less than, maybe it's both sides, more and less. Then we do the math. The math is going to give us a p-value. That's the probability of our sample that we got. Then we compare it to a cut score. If our p-value is smaller than, let's say, alpha 0.05, we would reject the HO and go with the alternative. If our p-value is greater than, then we would fail to reject the HO. All right, but that doesn't mean we accept it. Okay, one more piece of paper and then we should be good. When we do all of these hypothesis testing, sometimes errors happen. All right, so errors that could happen. That's not how you spell happen. 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 Errors that could happen. All right. So we've got this little chart that'll help keep it all organized. HO, true. HO, false. All right. I call this the Hot-Hoff chart. Hot-Hoff. The null hypothesis is true or the null hypothesis is false. Hot-Hoff. Right? Hot-Hoff. Okay. So either the null hypothesis is true or the null hypothesis is false. Those are our two options. And when it comes to significance tests, there's only two outcomes. Either we reject the HO, right? If the P is low, reject the HO. Or we fail to reject the null hypothesis. All right, so those are the two options. So if the null hypothesis is true and we reject it, oopsie, shouldn't have done that. It was telling the truth and we rejected it. We threw it to the curb. What we just did is called a type 1 error. If the null hypothesis was a lie, it's false, it's lying to us, and we rejected it, woohoo! We did good. Right? If the null hypothesis is true and we fail to reject it, means we keep it around, good for us. We did good because it's the truth and we didn't get rid of it. Last option, the null hypothesis is a lie, but we fail to reject it. We don't catch the lie. Oh man, if you don't catch the lie, that's called a type 2 error. Okay, so back to this type 1 error. The probability of a type 1 error is the same as the alpha level that you choose for your problem. So that significance level that you set at the beginning, 0.05 is the most common, 5% chance then of committing this type 1 error. So now you might kind of see why statisticians, researchers would want this cut score to be really low, because you don't want to make an error. Type 2 actually plays off of this thing called power. Right here, this box, this is called power, the power of a test. You don't have to worry about calculating it. It's going to be given to you in these problems. So when would we use it? Right here, a type 2 error. The probability of type 2 error is the complement to power. So it's 1 minus the power. So if there's a 90% chance of getting it right, 90% power level, then that means there's a 10% chance of getting it wrong. So these two go hand in hand. All right. Final thoughts. There are ways to increase the power. So increase your power. All right, there's two ways to make sure you got a powerful test. One way is to take a larger sample size. Take a larger sample size. That's usually the easiest, most cost-efficient, right? Just get out there and sample more, because we all know what happens when you sample more. The skinnier you get. That means less variability. Less variability means more consistent data, and everything falls into place. So larger sample size, and I'm going to put under parentheses, this all relates back to stats diet, trademark, get skinny people. And another way, all right, you could also increase your power by using a higher alpha level. So use a higher significance level, and the symbol for significance level is that alpha. So use a higher alpha, a higher cut score. If you have a higher cut score, a higher alpha level, it makes it easier, right? Makes it easier to reject the null hypothesis, right? So, I mean, I guess that's one way to get yourself more power, but if you're making it easier to reject, right, you're increasing your alpha, then you're also making it easier to commit a type 1 error. So I don't recommend, if you're in the real world, I don't recommend playing around with the alpha like that, right? Because, right, danger. A higher alpha means more of a chance for type 1 error. All right. So there you have it. All right, so that is the basic foundation of significance tests: null hypothesis, alternative hypothesis, p-values for your evidence, significance level alpha, and then of course your HOF, your errors that can happen after it's all said and done. I'm going to make another video that does some of the Khan Academy examples, because these can be a little tricky. So if you feel like you want more examples, tune in to video number 2, and I'll see you later. If I can figure out how to stop this thing. Ooh, wow, I look ridiculous. I love it.